All right, let's talk about radioactive sources, cesium-137. So what is this stuff and where does it come from? Well, it's a pretty common industrial radiography source. And where do we get it from? Well, it comes from a byproduct of nuclear fission. So we start with uranium and then it kicks off some xenon and then that degrades into cesium-137, which is going to turn into barium-137 over a period of time. But anyways, it comes out of uranium more or less. And it comes out of nuclear fission where we've got a controlled nuclear reaction. The half-life on this stuff's about 30 years. And we use it for gamma radiography on steel. We don't mine this stuff. It's a product of nuclear reaction fuel. It's a fission product. We don't go dig it out of the ground like we do uranium. It's a byproduct, a man-made byproduct.
Like I said, with a gamma source, once that gamma source comes out of the camera and it's to the point where it's exposing the film with gamma rays, they tape off whole areas of the area where you're shooting this radiography when you're doing radiography. Like I said, a lot of times they'll do it at night. The things you need to remember about radiation is time, distance, and shielding. So how long is it going to be exposed? What's the distance and how much shielding? So for protection of people, one of the big things is just distance. All right, we get enough distance between the radioactive source and where we've got people, there's no problem. And, they'll take into account if they're inside a giant building made of concrete or underground or something. But the big thing is distance. And a lot of times they'll tape off whole areas to keep people out of those areas when they're shooting radiographs, when they've got a gamma source that's exposing. Well, they're shooting X-ray or they're shooting radiographs. They're doing radiography. So here's the half-life of cobalt 60. So you can see our half-life is, 5 years. So after 5 years, you still got 50% of your radioactivity remaining, and then that gets cut in half after another 5 years. Another 5 years, it's cut in half again, and you can see how this keeps going on down until you asymptotically approach zero. You'll never hit zero, but you'll get pretty close. But this one's got 5.5 years or 5.25 years of half-life. Cesium-137. Now this is a byproduct of the fission process, and it has a half-life of 30 years. It's going to be used in radiography of steel thicknesses between 1 and a couple inches. It's superior to other isotopes of similar capability, only in its slow rate of decay. It's going to be around for a while. We're going to use it in a chloride. Remember I said it was a cesium chloride salt. It's a soluble powder requiring special safety precautions. Yeah, anything that can dissolve in water, you're going to have some special precautions, because if it dissolves in water, you're going to have you have the opportunity to have something really messy. The U.S. Nuclear Regulatory Commission wants this stuff double encapsulated in containers conducted of silver brazed stainless steel. Well, they want it double encapsulated because this stuff is a salt and soluble in water. So if it dissolves in water, you've got some contaminated water that you need to deal with. So you really don't want this stuff getting out. And the other stuff, a lot of the other materials are in the form of an oxide or just in the pure metal, and they're not going to dissolve in water like this stuff, like cesium-137 would. So where is cesium-137 used? Well, every isotope that we use for industrial radiography, it all has a thickness range that we can use it in. Some's just too big and others are too small. So generally these things have a very narrow band that we use them. So for cesium-137, steel, inch to 2.5 inches thick.
Much less than that, it's too much power. Much more than that in thickness, much more than about 2.5 inches, it just doesn't have the power to punch through. So where would we use this? Pressure vessels, big structural welds, and heavy fabrication components. So what are the benefits of using cesium-137? Well, it's got a really long source life, like 30 years. So, and it's going to give us a consistent output over that time frame. It's not going to degrade. Some of these sources have a half-life of maybe a year or two, so they degrade very quickly. And this leads to us not having to replace it very often. And we have nuclear reactors running, so we don't have to mine this stuff. It just gets processed from nuclear reactor production. And one of the major things, like I said, is longevity. So these things can, these cameras that use this is a picture of a camera, an isotope camera is what it's called. But anyways, these can run for a long, long time. 30 years is the half-life, and I don't know if you're going to run it 30 years. But anyways, you can run it a significant amount of time without changing the source out, which is a huge advantage over some other sources. So like anything else, we've got drawbacks and challenges. Here's a comparison of cesium-137 and cobalt-60. So you can see the half-life of cobalt-60 is 5.271 years. Cesium-137 is 30.07 years. The photon energy, you can see there's a huge difference here. 1.17 and 1.33 is what we're getting for photon energy in cobalt. That's why we use cobalt. It's the big boy. We can punch through some pretty heavy material with cobalt that we can't with cesium-137. So you can see that these would be some of the advantages and disadvantages. It's going to have lower gamma energy that we just talked about, that photon energy, than something like cobalt-60. It's going to have a limited thickness range. We talked about that on the previous slide. Not great for thick sections, and there's going to be special handling requirements. And thing to remember with these sources, just because it lasts longer doesn't mean that it's produces the best image quality or is best for that application. It just has a longer shelf life. Just because it's longer shelf life doesn't mean it's the best source.